And talk about some of the developments that are taking place right now, sort of push beyond 32 nanometers. What's the next step?
Well, the next step is basically to continue working on new materials to improve transistor performance, but also look at more novel structures such as the tri-gate transistor and other things. So there are several options on the books for future technologies.
Okay, now tri-gate sort of moves the transistor from the bulk up onto the surface. What's that going to do for us?
That gives you higher speed, lower power consumption, there's lower leakage, and potentially, including gives you higher density and potentially reduced variability in devices.
So we get a better transistor when we do that.
That's correct.
All right. So, okay, moving up to the surface. When you move up to the surface, I assume you're not limited to silicon. You can use other kinds of materials.
Well, there are other materials such as compound semiconductors, quantum well structures. There are a lot of options when you get to
3-5 kind of
3-5 type materials, gallium, indium, arsenide, other types of materials like that.
Okay, and what are their advantages?
They basically allow electrons to move much faster.
Okay.
And by going to lower voltages, you can also potentially have higher energy efficiency with the improved speed.
Okay. But now those are, I mean, they're still CMOS devices in some sense.
That's correct.
So, what happens when we get to the point where we just can't scale those devices, those CMOS devices anymore?
Well, we're going to keep pushing as far as we can. I don't know what that point is.
I know, you guys never want to let go of CMOS.
That's correct. We think that CMOS will still be the workhorse for many years beyond in the future.
Okay,
but there are options.
All right, tell us about it.
And we're looking for some options for novel state variables, such as electron spin, magnetic memory, molecular devices.
Okay, so moving away from electronic charge now to other quantum effects.
We think that actually the CMOS will probably be the platform, and then we'll have other functions on top of that, the other things such as other state variables. And then we'll have, and it may enable some new computing functions, more than maybe 2 states at some point. Maybe
moving beyond binary logic, is that what you're talking about?
That's correct. Possibly moving beyond binary logic. There are other things such as quantum computing and things like that could have multiple states.
Okay, so, there's a lot of talk these days about carbon nanotubes and graphene. Tell us a little bit about those kinds of materials.
Okay, those materials do have extremely high velocity for electrons. They can support very high speeds, and so they could enable lower power operation, higher computing speed, but also they have spin functions. So you could actually have a combination of electronic transport and spin properties at the same time.
I see.
They're some of the types of things we're looking for.
Okay. It sounds like there are a lot of options here.
There clearly are a lot of options.
How do you sort through all of those options?
Well, we are working with the Nanoelectronic Research Initiative, which is a consortium of the National Science Foundation, several federal labs, Intel, and others, working in 4 different centers that are sponsored by state governments and federal to identify innovative concepts and devices.
So this is really an industry academic collaboration of some scale.
That's correct. It's a very large organization of 4 major centers all working, coming up with innovative ideas to develop spintronics. At UCLA, they're working on spin-based devices.
Now, aren't there European activities along that line as well?
Yes, there are.
That we're part of too.
We're participating in Europe with IMEC and Leti and a couple of things, as well as a center in Ireland called Crown. Actually, we should pronounce it properly, Crown.
All right.
So but it is not one singular research effort in Europe.
Well, this sounds like, for a materials person, this sounds like a very exciting time. I mean, we basically were building that one transistor for many, many decades, and now it looks like there are a lot of options on the table.
Justin, this is really an exciting time for materials. It's like if you're looking for the beyond CMOS, we're back in the 1940s trying to invent the new transistor, developing new materials to support the new concepts.
Well, when you get one of these things, come on back and we'll have you up on the stage and you can tell us all about it.
We'll bring a university in to show.
All right.
Thank you.
Thanks, Mike. Mike Garner.